Hello, good afternoon. So today we are going to see an introduction to tree data structure. So we know that tree is a non-linear data structure. So today we are going to see a small introduction to the trees, its basic terminologies. So let us go ahead and see what we are going to see today. So these are the topics that we are going to see today. That is basic terminologies of the tree. Then what is a general tree? Then what is a binary tree, and then the representations of tree, that is sequential organization and linked organization. So let us see what are the basic terminologies. So here let us get introduced with the tree first. So a tree, as we know, it is a data structure, right, which is a type that is non-linear data structure. And why it is called as non-linear? Because it does not store data in a sequential memory locations. Okay, so the memory locations are not sequential. They are anywhere in the memory, but we connect them using the pointers. That is, the address of next memory location will be available on its previous memory location, right? So that is a tree. Now it is also has an hierarchical structure. So why it has an hierarchical structure? Because the elements in the tree are arranged in multiple levels. Okay, so initially there is a root on level 0, and then the children of the roots, that is, will be available on level 1 and so on. So the topmost node is known as root node, and each node in the tree contains some data, and this data can be of any type. Like it can be only integer, only character, or only float, as well as it can be combination of integer, characters, floats, strings, etc. Right? So this is a tree. Now let us go ahead and see the basic terms in tree, like what is a path. So as we can see, path. So path is nothing but a sequence of uh, edges connecting nodes, or a sequence of nodes along the edges of the tree. So here we can see in the figure below, that is in this tree. So here we can see the path can be like P to Q is also a path, as well as from P to Q, Q to A to L, L to E. So P, Q, A, L, E. It is also a path, as well as P, Q, A, L, F. It is also a path. P, R, C, M, I is also a path. So basically, path is nothing but a sequence of nodes along the edges of a tree. Now, what is a root? The node at the top of the tree is called as the root, and there is only one root for each tree per tree, and one path from the root node to any node. So from root node we have a single path to any node, and each tree will have a single root. Like here you can see in this diagram, P is a root node. P is a root node, right? As well as we have path from root node, like to agar if we want to go to G, so like P, Q, A, L, G. If we want to go for H, so it is P, R, C, M, H. So each node will have a path from root node. So that is a path and a root node. Now, what is next term, and that is parent. So the any node except the root node has one edge upward to a node called as parent, right? So generally a parent node is nothing but a node who have some children. Okay, so it is necessary that the node should have at least a single descendant or more than one descendants. Then that node is called as parent. Similarly, what is a child node? The node who has upward parent, a parent node. So that is called as child, right? And there is a leaf node also. So what is a leaf node? The node who don't have any child. Okay, so if the children of a node are 0, so that node is called as leaf node. So a parent node is a node who have either one or more children. Child node is a node who has a parent node on the upper level, and a leaf node is a node who have no children, 0 children. So that node is a leaf node. And root node is a node which is the topmost node of a tree from where the tree starts, right? So we will see all these nodes here in the diagram. So P is a root node. Now Q is a parent of A and B. So A and B are the children of Q. A and B are the children of Q. Similarly, C and D are the children of R. And Q is a parent of AB, node A and node B. R is a parent of node C and node D. Similarly, L is a parent of E, F, and G, and E, F, G are the children of L. Now, let us go ahead and see what are siblings. So, siblings are nothing but children from the same parent, like A and B are siblings because they are having a same parent, and that is Q. Similarly, E, F, G are siblings because they are having a same parent, and that is L, right? Now, nodes E, F, G, H, I are leaf nodes because they are having 0 children. Similarly, node B for banana, that is node B, is also a leaf node, right? Because node B also have a 0 child, 0 children. Node D is also a leaf node, right? So these are the some terminologies, and you can see each node has some data, and this node is connected to other nodes through edges or pointers. Now each node has some data which can be used to search that node, and that is why this data is called as key, right? So these are the some terms. Now what are others? So you can see here subtree. So subtree represents the descendants of a node. So subtree means it's a part of a tree only, and it is just a subset of nodes. So if tree consists of 10 nodes, then a subset of those nodes is called as a subtree. So like here you can see we have shown by a dotted line in blue dotted line, like L, E, F, G. So L is a parent, E, F, G are the children. So here this a small tree is called as a subtree of this of this main tree, as well as if we can start from R. So R, C, D, M, H, I. R, C, D, M, H, I. So this is also a subtree, right? This is also a subtree. Now let us go ahead and see what is visiting and what is traversing. So visiting is what? Checking the value of a node when we are on that node. Okay. So when the control is on that node, then accessing or checking the value of a node is called as visiting the node. And what is the traversing? Passing through nodes in a specific order. Passing through nodes in a specific order is called as traversing. Like in tree, we have pre-order traversal, in-order traversal, post-order traversal, then depth first search, and breadth first search. So these are the 5 types of traversals available in trees. So let us see here what is visiting. So if I start accessing the nodes of this tree from root, so when I'm on root, I'm accessing the data P. So that is called as I'm visiting P. Now from P, if I shift my control to the Q, so that means I'm visiting Q. Now from Q, if I'm shifting my control to A, so that means I'm visiting A, and so on, right? So this is when we shift our control from one node to another and to access that node. So that is called as visiting the node. Now what is traversal? That is passing through the nodes in a specific order. So what is a specific order? Like consider BFS. So breadth first search. So what is BFS? It is level wise traversal. Like you can see, initially we will visit P, then Q, then R, then A, B, C, D, then L, M, then E, F, G, H, I. So we are traversing the nodes in a specific order, and that order is level wise. And this order is called as breadth first search. Okay. Now there is one more order as an example, and that is depth first search. So in depth first search, I will start from the top, that is root, and every time I will go from top to bottom, again from top to bottom, and so on. So that is PQALE, then F, then G, then B, then R, C, M, H, then I, then D. Okay, once again, P, Q, A, L, E, then F, then G, then B, then R, C, M, H, then I, and then D. So this is depth first search. Okay, so this is also a type of traversal. So passing through the nodes in a specific order is called as traversal. And when we are on a particular node, that is called as visiting that node, right? Now, after visiting and traversing, we have levels. So what is a level? So the root is considered as on level 0. Now the children of the root are on level 1. Its root's grandchildren will be on level 2, and so on. Okay, so what is the level here in the diagram? So you can see root P is there, and who is on level 0. Now Q and R are the children of level root P, so they are on level 1. On level 2 there is A, B, C, D. On level 3 there is L and M. On level 4 there is E, F, G, H, I, right? So again I will repeat this. On level 0 there is always a root. So root is always at level 0. On level 1, children of root, that is Q and R. Then grandchildren are on level 2, that is A, B, C, D. Level 3, L, M. Level 4, E, F, G, H, I. Right? So this is how we have 4 levels here: 0, 1, 2, 3, 4. So height of the tree is the highest level. So the highest level is 4, and that is why height of the tree is 4. Right? So this is one more, that is height of the tree. Now what is key? So key represents a value of a node. Key represents value of a node based on a search operation. Like in this tree, if I want to search Q, so I will start from P, then I will go to the left of the P and I find Q. So Q is a key, right? So Q is a key. That means the data part of a node consists of some values, right? For example, each node of each memory location allocated for a node, each memory location allocated for node will have two parts. First part is a data part and second part is the address part. So in data part, we have number of values, and out of those number of values, one value may act as a key. So that value will be used while searching, right? So that value is called as a key value, which we can use while searching, right? So like if I want to search for M, so I will start from P, then I may go in left initially, like Q, A, B, I won't find it there. So I may come on the right, and then after R, C, I will get M. So M is a key to search, right? So this is a key. So these are the terminologies that we have seen here. What is a root node? What is a parent node? What is a child node? What is a leaf node? Then we have also seen what are levels. Root is always at level 0. Then level 1, 2, 3, and so on. Highest level is nothing but height of the tree. Then we have siblings, children from the same parents. Then we have subtree. It is just a subset of nodes from the given tree, right? Having a parent and children relationship. So that is a subtree. Now we have age, that is a pointer connecting the nodes. Then we have path, number of nodes or sequence of nodes along the edges of the tree. Then key, that is the data part of a node. Then we have siblings, children from the same parent, right? So these are all the terminologies which are used Now there are two more, that's internal nodes and external nodes. So internal nodes are the nodes except root node and leaf node. So between the leaf nodes and root node, there are some nodes. Those nodes are called as internal node. And except root node and internal node, the nodes are there and they are called as external nodes, right? So these are internal and external nodes. Like here, E, F, G, B, H, I, D are external nodes, which are also called as leaf nodes. Now we have this example of general tree. You can see here. So what is the general tree? In general tree, any node can have any number of branches, any number of children. It can be 0, 2, 4, 8, 10, anything. So that is called as a general tree. This is one more example of general tree where you can see root node have 3 children. Now first child of the root have 3 children. Second child of the root have single child, and third child of the root have 2 children. So any number of children are possible in a general tree. So we have a binary tree, which is a type of a tree. And here the number of children possible for each node are either 0, 1 or 2. So maximum 2 children possible for each node. So either a node will have 0 children or a single child or 2 children. Like you can see in the example, node 2, which is a root node, have 2 children, 4 and 10. Now 4 also have 2 children, 6 and 5, and 10 has a single child, that is 11. Now 6 and 5, 6, 5 and 11 have 0 children, right? So this is a binary tree. Okay. So binary tree is a type of tree where each node can have 0, 1 or maximum 2 children, right? So now we have some types of binary trees also. Like we have a full binary tree, complete binary tree, degenerate, perfect and balanced. So let us see what is a full binary tree. So full binary tree is a binary tree where each internal node of the tree will have exactly 2 children. Each internal node of the tree, that is binary tree, will have exactly 2 children. So you can see root node have 2 children, then its child's left child also have 2 children. So all the internal nodes are having 2 children. Okay, and the remaining nodes are leaf nodes, right? So there are 4 leaf nodes on the last level, and the level before the last also have 2 leaf nodes. So except leaf nodes, all the nodes are there in the tree will have exactly 2 children. So that is called as full binary tree. So similarly, there are different types of binary trees like complete, degenerate, perfect, and balanced. So in perfect binary tree, you can see all the leaf nodes should be on the same level. All leaf nodes should be on the same level, and all internal nodes should have exactly 2 children, right? So that is called as perfect binary tree. So these are the different types of trees that we have seen now. And now we will go for tree representations. So how we can represent tree? Like we have represented stack using array or using linked list. We have represented queue using stack or using linked list. Okay, based on that, we have called it as linked stack or linked queue. So now we have same, that is 2 representations, sequential representation and linked representation. That is, we are going to represent tree. We are going to store the nodes of the tree, data of the tree using array and using linked list. So if we are storing it using array, it is called as sequential organization, because we are going to store the data in sequential manner in the memory, sequential or contiguous memory locations. So here you can see the tree here, binary tree, having nodes which will have maximum 2 children. So A has B and C, 2 children. B has D and F. D has I and J as a children. F is a leaf node, so no children. G has right child, not left. And C has G and H, right? So in binary tree, as any node can have maximum 2 children. So while storing this tree, we will start from root. So root is A. So store A in the first memory location of array. Then when you are starting from A, so C, which are the children of A. So there are 2 children of A, that is B and C. So for each node, we will have 2 memory locations for its 2 children. So for A, we have B and C, right? So store B and C as the children of A. Then store the children of B. So who are the children of B? That is D and F. So store the children of B, that is D and F. Then store the children of C, that is G and H. Then store the children of D, that is I and J. After D, go for F. So store the children of F, and you can see there are no children for F. It is a leaf node. So just leave the 2 memory locations of array empty, because maybe in future we will insert the number of nodes as the children of F, and they cannot be more than 2. So just leave 2 memory locations empty. Now after F, insert the children of G. Now G don't have left child, so leave 1 memory location for left child empty, and then right child is K. Insert K in array. Then after G there is H, which is again what, a leaf node, right? So just leave 2 memory locations. After H there is I, which is again a leaf node. So just leave 2 memory locations empty, and then J. Okay, so J is also leaf node. So again leave 2 memory locations. So this is how for each node in binary tree, we leave 2 memory locations for its left child and right child. So this is how a tree can be represented using array, right? Now it is a binary tree, so it is, we know that there are 2 children, but if it is a general tree, then what? Then it is better to store the existing nodes in the array. And when it is modified, we can create a new array to store the modified nodes or the number of nodes in the modified tree, right? So it is like in binary tree, we are leaving the empty locations, but in general tree, instead of leaving the locations, as we don't know how many so how many children a node going to have, so it is better to not leave empty locations. So let us go for now linked representation, and you can see here in linked representation we are using doubly linked list, where each node will have a data part and 2 address part. So as we are starting from A, so data part is A. So on the left side of A there is a left pointer, and on the right side of A there is a right pointer. So a single memory location will consist of a data part and 2 address parts. So one address part will hold the address of left child, and another address part will hold the address of right child. Like A has a left pointer for B and a right pointer for C. Similarly, node B, which is a left child of A, has 2 children, that is D and F. So B has left pointer for D. It is storing the address of D in the left pointer, and it has right pointer for F. Similarly, for D has a left pointer for I, right pointer for J. Now C has a left pointer for G and right pointer for H. And now you can see G has a left only right child. So there is a right pointer and left pointer is null. Similarly, I, J, F are leaf nodes. They have their left and right pointers null. Now similarly, K and H are also leaf nodes. The left and right pointers are null, right? So this is how we can use doubly linked list to represent binary tree. So these are the 2 representations: sequential representation using array and linked representation using linked list. So if we have a general tree, the number of pointers will increase depending upon the number of children of the node. So this is what we have seen today in the lecture of introduction to tree data structure. So initially we have seen the definition of tree, then we have seen the basic terminologies of the tree, like what is the root node, what is parent node, what is leaf node, then what is the child node, then what is subtree, what are siblings, then what is level, what is height of the tree, what is key, what is node, what is age, what is path, and so on. And after that we have seen the general tree, then the concept of general tree, then binary tree, types of binary trees, and then at the end we have seen the representations of tree, that is using sequential organization and using linked organization. So I hope you enjoyed the lecture. So have a good day. Thank you.